Section 5 is about the dissociation of water. You'll be able to use the water dissociation expression to calculate the hydronium ion and the hydroxide ion concentration in an aqueous solution. In pure water, a forward reaction between two water molecules transfers a hydrogen ion from one water molecule to the other. Check this out. If I've got water and water, obviously one of them will donate a proton to the other. So one water molecule will be left with one less hydrogen, which would be our hydroxide, and the other water molecule will grab that H and will be H3O+. The hydronium and hydroxide react in the reverse direction to reform two water molecules. In the reaction between two water molecules, equilibrium is reached between the conjugate acid-base pairs, which is shown by the double arrow. One water molecule, like I said, is going to donate to give us on the right side the hydroxide ion. So on the left it has more hydrogens. We call it the acid. It's the hydrogen donor. On the right, that is our base. It's our hydrogen acceptor. Now we could have just as easily made this water the base, the hydrogen acceptor. So it doesn't matter which one you made the hydrogen donor, but whichever one you made the hydrogen donor is the acid, and the one that you made the hydrogen acceptor is the base. Now this water became our base. It was the hydrogen acceptor, so its conjugate pair over here is the H3O+. That's our acid. Now we will be able to write the water dissociation expression called Kw. Using the equation for the reaction in water at equilibrium, we can write, using this, our K water dissociation expression. By doing this, we write the concentration of our products. Our products are H3O+ and OH-. And to show concentration, we show those brackets. Products over reactants. Omitting the constant concentration of pure liquid water gives the water dissociation expression, which is this. Kw is equal to our hydronium ion concentration times the hydroxide ion concentration. Experiments have determined that in pure water, the concentrations of hydronium and hydroxide are each 1.0 times 10 to the negative 7 molarity. So pure water is telling us that the hydronium is equal to the hydroxide, which is 1.0 times 10 to the negative 7. And remember, concentration, capital M, molarity, is moles per liter. So when we write, our Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. And each one of them is 1 times 10 to the negative 7. If I do 1 times 10 to the negative 7 times 1 times 10 to the negative 7, we get 1 times 10 to the negative 14. That is water's dissociation constant. When the hydronium ion concentration is equal to the hydroxide ion concentration, our solution is neutral. In this case, if they are both 1 times 10 to the negative 7, then we have pure water, we have a neutral solution. If the hydronium ion or the acid is greater than the base, then we have an acidic solution. If our base is greater than the acid, we have a basic solution. Remember, in neutral, basic, and acidic solutions, our Kw is always equal to 1 times 10 to the negative 14. So in an acidic solution, we can see here that our hydronium ion concentration is much larger than the hydroxide. When we have a neutral solution, they are the same. And in a basic solution, our hydroxide ion concentration is larger than the hydronium ion. Here are just some examples of hydronium ion concentrations and hydroxide ion concentrations. Make sure and notice that the Kw for all of them is 1 times 10 to the negative 14. This times that is always going to be equal to our 1 times 10 to the negative 14, our water constant. Again, neutral, these are both going to be equal. In an acidic solution, this is larger than our hydroxide. But again, they still equal 1 times 10 to the negative 14. Here's another example of an acidic solution is greater than the hydroxide ion. And these two are both basic. So our hydroxide concentration is going to be greater than the hydronium. If we know the hydronium concentration of a solution, we can use the Kw to calculate hydroxide. Here is our starting. If we need to find hydroxide, we just divide both sides by H3O+. So hydroxide is equal to Kw divided by the concentration of our hydronium ion. We could also calculate the hydronium ion concentration. All we would do is divide both sides by hydroxide. Let's do a quick problem. A vinegar solution has a hydroxide concentration of 5 times 10 to the negative 12th molarity at 25 degrees Celsius. What is the hydronium ion concentration of the vinegar solution? Is it acidic, basic, or neutral? I started the setup here. We know that Kw is equal to the concentration of our hydronium times the concentration of our hydroxide. We know that Kw is 1 times 10 to the negative 14. We don't know H3O plus, that's what it's asking us to find. We're given hydroxide ion concentration. So to get H3O plus by itself, we're going to get rid of this 5.0 times 10 to the negative 12. So in your calculator, can you do 1 times 10 to the negative 14 divided by 5 times 10 to the negative 12? And my calculator spit out 0.002, and we could write that in scientific notation, which would be 2 times 10 to the negative 3. And again, that's molarity, which is moles per liter. We could double check this by taking this answer and timesing it by 5 times 10 to the negative 12, and we should get 1 times 10 to the negative 14. That wraps up this section, so take a minute to look over the review and make sure that you understand the learning goal. In section 6, we are looking at the pH scale. You'll be able to calculate the pH from the hydronium ion concentration, or given the pH, you can calculate the hydronium ion concentration and the hydroxide ion concentration of the solution. In the environment, the acidity or the pH of rain can have significant effects. When rain becomes too acidic, it can dissolve marble statues and accelerate the corrosion of metals. In lakes and ponds, the acidity of water can affect the ability of plants and fish to survive. The acidity of soil around plants affects their growth. If the pH is too acidic or too basic, the roots of the plant cannot take up some nutrients. Most plants thrive in soil with a nearly neutral pH, although certain plants like orchids, camellias, blueberries require a more acidic soil. Although we have expressed H3O plus, or hydronium ions, and hydroxide ions as molar concentrations, it is more convenient to describe the acidity of solutions using the pH scale. On this scale, a number between 0 and 14 represents the hydronium ion concentration for common solutions. If we have a solution that's neutral, it has a pH of 7, and this is at 25 degrees Celsius. If we have an acidic solution, its pH is less than 7, and if we have a basic solution, its pH is greater than 7. So a pH of 0 would be an example of 1 molar of hydrochloric acid. Then we have gastric juice, which is found in our bodies. Then we have lemon juice at 2.2, vinegar 2.8, a carbonated beverage, a pop that you drink, at 3, oranges 3.5. Then we have apple juice, tomato juice, coffee, bread, potatoes, your urine, milk. All of those are acidic solutions. They're all less than 7. Then we have neutral is 7, pure water. Drinking water is at 7.2. Our blood plasma is at 7.4. Bile, detergents, seawater are all basic. Milk of magnesia is at a 10.5. Ammonia, common household glass cleaner, bleach, and at 14 we have 1 molar of sodium hydroxide solution. How do we test for pH? Well, the pH is determined by using either a pH meter, pH paper, or indicators that have specific colors at different pH values. Consider the pH for the following bodily fluids: your stomach acid, pancreatic juice, sweat, urine, cerebrospinal fluid. Place the pH values of the body fluids on the list in order of most acidic to most basic, and tell me which body fluid has the highest hydronium ion concentration. The most acidic body fluid is the one that has the lowest pH. The most basic one is the highest pH. So going from lowest pH would be our stomach acid, then sweat, then urine, then cerebrospinal fluid, then our pancreatic juice. And the body fluid with the highest hydronium ion concentration would be the lowest pH value, which would be our stomach acid. Let's calculate the pH of solutions. The pH is defined as the negative logarithm of the hydronium ion concentration. So This is an equation you're going to want to write down, the negative log of the hydronium ion concentration. Let's say that our hydronium ion concentration was 1.0 times 10 to the negative fourth. We're simply going to take our calculator and type in the negative log of 1.0 times 10 to the negative 4. And that would give us 4. If that is confusing, try just typing in the log of 1 times 10 to the negative 4, and that would tell you negative 4. And then we'd just bring down that opposite. The opposite of negative 4 is 4. When we express pH values, the number of decimal places is equal to the number of significant figures in the coefficient of that hydronium ion concentration. For example, if my hydronium ion concentration was 1 times 10 to the negative 4, and I typed it into my calculator, I would have 1 digit after that decimal. My calculator would spit out 4, so I would say 4.0. If my hydronium ion concentration was 2.4 times 10 to the negative 8, my calculator is going to spit out a bunch of numbers, but I'm going to have 2 numbers after that decimal, so 7.62. If I had, again, 2 sig figs, I'm going to have 2 after my decimal. And this top number, that exponent, is going to tell me that I would have 1 whole number. This shows in real life. We would use a dipstick to measure the pH of a urine sample, and if soil is too acidic, nutrients are not absorbed by the crops. Then lime, or calcium carbonate, which acts as a base, might be added to the soil to increase the pH. Here's a sample problem. Acetylsalicylic acid, which is aspirin, was the first non-steroidal anti-inflammatory drug used to alleviate pain and fever. If the solution of aspirin has a hydronium ion concentration of 1.7 times 10 to the negative 3 molarity, what is the pH of the solution? Well, we're going to start with this equation. The pH is equal to the negative log of the hydronium ion concentration. So the negative log of 1.7 times 10 to the negative 3. Here's what you would use for your calculator if you have a scientific calculator. 1.7 EE, or exponent, raised to the negative third, and then you can hit the log and the plus or minus button and then hit equals. Or you can hit negative log of 1.7 times 10 to the negative 3 equals, and we would get this big long calculator display. Since I started with 1.7, I'm going to go to 2 decimal places, and because this is negative 3, that's 1 number, we're going to just have that 1 whole number for our final answer. Now the pOH scale is similar to the pH scale, except that pOH is associated with the hydroxide ion concentration, and we find it the same way. The pOH is equal to the negative log of the OH. If we have a high hydroxide ion concentration, then we'll have low pOH values. If we have a low hydroxide ion concentration, we'll have high pOH values. In any aqueous solution, the pH of a solution plus the pOH of a solution will equal 14. We could find the pOH simply by doing 14 minus the pH. So if I was told that we had a solution with a pH of 3.5, the pOH would be 14 minus 3.5, which would be 10.5. Here's just a comparison chart showing us pH and pOH values and how they relate to one another. You can play around with these values, but if I know the hydronium ion concentration is 10 raised to the 0, if I did the negative log of that, I would get a pH of 0. If my hydroxide ion concentration is 1 times 10 to the negative 14, took the negative log of that, I would get a pOH of 14. Notice that pH plus pOH is going to equal 14. Same for all of these. 1 plus 13 would equal 14. If I went down here, my hydronium ion concentration 10 to the negative 8, I would have a pH of 8. 10 to the negative 6, I'd have a pH of 6. 8 plus 6 is going to give me 14. What is the pH of an ammonia solution with a hydroxide ion concentration of 3.7 times 10 to the negative 3? Well, we could do a couple of things. Do you remember that Kw is equal to the concentration of H3O plus times OH minus? If we're given the hydroxide ion concentration, we know Kw is 1 times 10 to the negative 14. We could find this and then take the negative log of it. Or we could take the negative log of our hydroxide ion concentration and then simply do 14 minus that answer to get our pH. It's up to you. Let's do both. Here's the one way, using kW. We know hydronium times hydroxide is 1 times 10 to the negative 14. So to solve for H3O plus, we do 1 times 10 to the negative 14 divided by 3.7 times 10 to the negative 3. And I would get a hydronium ion concentration of 2.70 times 10 to the negative 12. And the negative log of 2.7 times 10 to the negative 12 would give me 11.57 with the correct number of sig figs. Let's do it the other way. If I find the negative log of the hydroxide ion concentration, that would give me my POH. And the negative log of 3.7 times 10 to the negative 3 is 2.43. Then, to find the pH, we do 14 minus the POH. That'll give us our answer. So let's try 14 minus 2.43, and that would give us 11.57. What if I want to work backwards, calculating the hydronium ion concentration from the pH? Because we just found the pH from the hydronium ion concentration. All we have to do is take 10 raised to the negative pH. If we're told that we have a pH of 3, we simply just do 10 raised to the negative 3, which would give us 1 times 10 to the negative 3 molarity. Let's try this sample problem. We want to find the hydronium ion concentration for a urine sample that has a pH of 7.5. We're simply going to, in our calculator, type in 10 raised to the negative 7.5. And if you put that into your calculator, we should get 3.16 times 10 to the negative 8 molarity. You could type in either of these calculator procedures, giving us our answer of 3 times 10 to the negative 8 molarity. Take a minute to look over the review and make sure that you feel comfortable with this section.